event that we hold once a year in memory of one of our colleagues who passed away very prematurely, Professor Robert Dexter. It's my great pleasure to introduce our speaker today, Professor Robert Conner from Purdue University, who knew Robert very well as a colleague and friend. They were together at Lehigh University for a number of years. And I think that's where you first met, and that developed a long collaboration between the two of them and studying a lot of topics related to fatigue and fracture of steel structures. Professor Conner, after his career starting at Lehigh University, spent some years there as a senior research individual at the laboratory, where he studied fatigue and fracture there before moving on to Purdue University in 2005. There he's a professor and has won numerous teaching awards, and also was recognized by AASC for all of his contributions to fracture. So without further ado, it's my great pleasure to introduce our speaker.
Thank you, Kathy. Appreciate it. Well, thank you very much for the honor of coming. See, I can't talk about Robert without two things happening: getting teared up, which is happening now, or laughing like crazy. Because if you knew Robert, and I know some people here did, everybody has a Dexter story. And sometimes it involved the police. Sometimes it involved getting snuck into snowbanks. There's any number of stories related to Robert, but he was a brilliant man, and he was a great mentor, and I was honored to know him, so it's a privilege. So one of the topics that he and I worked on right before his death, all the way back to 2004, was this idea of fracture-critical bridges. And just by a show of hands, how many people know about bridges, the idea of fracture-critical, what that means, because it kind of gauges what I should talk about. So, okay, I'll give you a little background. So fracture-critical bridges are a whole classification of structures, steel bridges, that if they have a tension member, right, something subjected to tension, the concern is if that member were to fail in fracture, it'd be very critical, which is usually bad, right, fracture critical, that the bridge, and this is where the definitions get weaselly, right, probably would collapse, could lead to collapse, may result in collapse. The classic example is the Silver Bridge over the Ohio River back in the 60s that had collapsed and led to a lot of the inspection and toughness requirements we have today. But it was founded when bridges, you know, if you think about the policies were put in place in the 70s, well, that's based on information from prior to that, right? The type of steel we used, the type of design, what we knew about fatigue and fracture at the time. And so fast forward now to 2004, still quite a while before. It was recognized by some people, Robert being one of them, that it isn't 1967 anymore, right? We're not building bridges of the 1950s anymore. And maybe we could do something different with this family of structures. Now why? What does it matter? This family of structures are subjected to a lifelong inspection strategy that requires arm's length inspection of every component, face, whatever you'd want to say, of that member. So if you had an I-beam that is deemed fracture critical, you have to be arm's length, Kevin and his folks have to be arm's length from both faces and looking, and what you're looking for are little cracks and things that are, as we can talk about, probably not likely to be found. So it's very expensive, but they're very efficient structures. There's really nothing wrong with them. In fact, their history would prove opposite, that they perform very, very well. So what this whole series of projects, I'm just going to hit a bunch of them, the idea of changing the thought process of fracture critical. And the reason I guess I say that is every aircraft you get on has fracture critical components. But that industry has wisely, first of all, never called them fracture critical to the public, right? And if you got on an aircraft down at Minneapolis, if you get on an MSP there and the pilot comes on and says, welcome, we're heading down to, well, let's not go to Florida. Nobody wants to go there today. We're heading to Palm Springs or something. On our fracture critical Airbus A320, there'd be a procession of people getting off, right? And so that was part of our fault, calling it something not so, maybe a little too scary. But we can address the fracture limit state, the fatigue limit state, like we couldn't many years ago. And so we've been fortunate at Purdue to have several projects that kind of grew out of a meeting that happened in 2004 to try to maybe rationalize some of this, that not to require this arm's length inspection every 24 months. Now, the interval of 24 months, for those who are bridge people, did anybody know the big research projects that were done to come up with the 24-month interval? Okay, I'll show you the research process. Literally, when the failures occurred, there was no real inspection program in place. And so the people who were, good people and trying to figure out what to do, they knew 1 year wasn't, that's unreasonable. It's too often. 10 years is too long. 24 months came about. And it's held in with fracture critical. And so there's no rationale to it. And so today, you could imagine that if you had a clean slate of how you would set an inspection interval, you'd probably put some engineering to it. Maybe you'd run some numbers, right? You'd think through it a little bit. And so that's hopefully where these projects will come together to have what's called an integrated fracture control plan. Now, I've been privileged to work with some really sharp people on this. I'm going to take credit for a lot of work here today, but there's been a lot of people involved. First of all, one of my colleagues, Amit Varma, who's a professor at Purdue, another Lehigh person who knew Robert very well. Dr. Lai, Jim Korkmaz, Frank Martin, Ryan. Ryan's now out at University of Nevada. He's a professor out there. And then Matt and Will Collins at their universities put a lot of time into these projects trying to rationalize fracture critical. But with that, I'll talk about this whole concept a little bit. So maybe a different title should be Designing a Bridge to Stay Up, because that's really what the objective is, right? Rather than give it some arbitrary label, fracture critical, we want it to be safe in various conditions, whether it's in a faulted state, maybe in the presence of a fracture, or maybe in its new state, right? We want it to be good then. So think of it that way. Don't use that title, but if something goes wrong, first of all, is it likely to go wrong? And if it happens, well, is there a way we can address that? And so the term that always gets thrown around is redundancy. Well, I want redundancy. But is redundancy the solution? In other words, if I have a 2-girder bridge, it's fracture critical, we'll say. If I have 6 girders, well, it's not, because I have more than 2 girders, right? I have redundancy. If I lose 1 girder, I have 5 more. But is that really controlling fracture? It isn't. I could have a very high likelihood of fracture with 6 girders. So that's not a fracture control plan. That's maybe a consequence or damage management plan or something along those lines. And the other issue, our current fracture control plan that we use to try to manage fracture is very fragmented in this country. And it's natural. Those things kind of happen, right? We're reactionary. So in other words, when the Silver Bridge failed, well, an inspection program was put together. But it wasn't really put together knowing much about inspection because there wasn't inspection data. There wasn't a lot of information about fatigue performance or fracture toughness. In other words, it wasn't all integrated. A good fracture control plan, really, a shortcoming in one area is made up in other areas. So let's say I can't have a material that's very tough. I can't tolerate cracks. Well, then that means I should be inspecting, or I should design, or I should do something to address that so that I can limit the consequence, or the risk, the overall risk, rather, of the fracture. And so a true plan tries to look at this, right? Link all this kind of stuff together. Sometimes it'll be referred to as damage-tolerant design, maybe. There's different terms for this and different approaches. But we make up for shortfalls in different areas. Now, there's a lot of ways to control fracture. And redundancy is only one way to mitigate the consequence of fracture. In fact, Robert had said, I remember talking to him about this, he's like, it bothered him that people would say, well, just because I have 4 girders, I'm not fracture critical. Because if those 4 girders were designed really right up to their limit, very efficiently, what happens if I lose one? I lose the bridge, right? Because I don't have any reserve left. And so this presumption that that just gets you something really isn't true. We rely upon it, but it really isn't true, right? And so redundancy is just a strategy to mitigate the consequence. And so I'll talk about a couple of projects, kind of higher levels of what's going on, looking at ways to address this, maybe try to link some of these things to control the risk and not just adding girders, because that's not a very economical way to do it necessarily. Now, when we look at risk, we have to remember that risk is made up of 2 things, right? There's the likelihood of something going wrong and the consequence associated with it. Very often we kind of think of only one, right? And we then throw the term risk at it, but it's really 2 things. And so something that is, if it happens and it's not a big deal, it's low consequence. If it's very unlikely to happen, well, that's low risk, right? But if something that's very likely to happen and the consequence is very, very bad, that's high risk. So if we can kind of control some of these, we can be down in an area we want to be, right? Regardless of how many girders we have, for example. So maybe on our likelihood side, we would say our toughness or how we detail, our stress ranges in fatigue, right? How we load the structure. On the consequence side, well, that's going to be collapse, right? If it happens, if something bad happens, is it loss of service or loss of life? And so maybe if we were to say, well, like, you know, a 2-girder bridge. If I lose one girder, it's likely I'd lose the bridge. Well, if I have really low toughness and high fatigue stress ranges and I have cracks, it's likely something is going to go wrong, right? And if it only has 2 girders, it's probably going to be bad. Now, today, we presume we're always in this column, that if I lose one of the 2 girders, the bridge will collapse. That's not the case. In fact, there's no examples in the literature of a 2-girder bridge that has ever collapsed. There was one right here, the Lafayette Street Bridge. We have it at our bridge center. 2-girder bridge, a girder fractured, and it was hardly perceptible. The bridge is a system. It's not your simple statics, pin trusses, and things like that, right? There's more examples of bridges that have failed that have had, who've performed well that would be classified as fracture critical. But let's say I do some kind of system analysis. We have some powerful tools today to look at this bridge as a system, not just a simple girder. Well, really, I could maybe show that my consequence of that failure now is low, that the bridge would stay up under some loading combination that I deem as acceptable. And even then, if I have, you know, poor details, well, I'm not in the high risk. And so I can manage this structure differently. But let's say I have the modern bridge, not the bridge from 1957. I have the bridge of today where I can show through analysis that I have redundancy, and I use really tough steels, the high toughness steels we have. I have designed it for infinite fatigue life. So my likelihood of there being a problem is low, and if it happens, the consequence is low, right? So that's low risk, and that's where we want to be. There's ways to do this, not just adding girders. So the goal is to really then just change how we think. And so, you know, the younger people here, you're the folks to be convinced. Because a lot of times, you know, the people who have been around this for a long time just say, well, they're fracture critical. They're just labeled that. But that's not really the case. So if we can address it in some rational way, something we all agree is thought through well in some engineering, really the term has no meaning, right? Because fracture is no longer critical. And the illustration I use all the time is, I can have a truss. The tension members are fracture critical. Why aren't the compression members buckling critical? Why didn't we ever label them that? Why? Has anybody taken steel design yet? Yeah. Professor Galambos may comment on, tell me I'm all wet with this statement. But folks did a lot of good research, mostly at Lehigh, right? I can say that because we're Lehigh. On columns. And we have equations and there's statistics. And they did a lot of work to say, I can calculate P critical with confidence. That's why we don't have buckling critical, right? We take in imperfections. We took all this stuff into account, or they did. We can do the same with tension members today. That's why we don't have buckling critical. We don't treat them separately. All I'm saying is we can do that today in 2016. And so we can get the reliability that we want to achieve. There's other things to keep in mind. Like I said, the historical performance of these bridges is excellent. And I say despite what your mother told you, right? Your supervisor told you. Because people have this feeling that these bridges are bad. Now, they're not. In fact, in this country, there were no fatigue provisions. You know, metal fatigue is if you take the paper clip, like if you're bored in a lecture like this, right? And you bend the paper clip. And eventually you have 2 pieces of paper clip. Well, we didn't have provisions for that in bridges, which are cyclically loaded all the time, until about the mid-1970s. Bridges then prior to that were never designed for that whole limit state, but they're not falling down because they perform quite well. So bridges that were never designed for fatigue. Bridges prior to what we call our modern fracture control plan. And that's really some more stringent fabrication and material selection. So some of the older structures with steel, it's not so great. They've even performed well when a fracture occurred, right? So the historical performance is good. In fact, the last study I worked on with Robert, we found no cases where there was pure fatigue and fracture issues that led to collapse. Now you might be thinking, well, you know, the silver bridge rather, well, you could argue that was one, but we don't build that anymore, right? Brittle, high-strength I-bars. 35W was not a fatigue fracture issue. The Mianus River Bridge, that's fracture critical, that collapsed, that was a corrosion issue with pin and hangers and maintenance. It kind of led to some fatigue issues, but it wasn't primarily that. And then the bridge out in Washington State, a truck hit the compression member bracing, and the compression members brought it down. So the cases that people point to, and 35W unfortunately became the whipping boy of fracture critical, had nothing to do with fracture, right? So we spent a lot of time on inspection. Every 24 months, arm's length, spending a lot of money. Would it have made a difference in the bridges that collapsed? The Silver Bridge, the flaw that led to the failure was about 1/8 of an inch flaw that was, you couldn't see it. So you could spend all day doing visual inspection on the bridge. You could look at it, say it's fine, and go home, and it's in the river that night because the inspection technique couldn't have found the defect. So we spend a lot of money on this. We have to ask ourselves, what is it getting us? Some other things. We spend time doing bridge inspections for safety, and we need to. But we have to think about probability of detection. What is the probability I can find that? And I talked to some of the students earlier today where the data that we've been collecting isn't very encouraging about the probability of finding a defect. And one of the studies one of my colleagues did it's 5 minutes. So if you have a queue of 5 minutes on interstate speeds, you start backing up traffic, you're 24 times more likely to have a serious accident. And so we're trying to protect the public, but we're also endangering the public by closing the lanes and the people doing the inspection, right? So we better be certain that what we're doing has meaning if we're going to put people's lives at risk in order to do it. So with all that history, there's several projects that we've been fortunate enough to be leading at Purdue. The first two are pooled fund studies where multiple states get involved and contribute. The first one is looking at the toughness of high-performance steel, which is just an industry name for steel that high performance. Well, it's got more toughness. It's got some good qualities, but the one that it has is toughness. Has anybody here ever seen a Sharpie impact test? Right, the little specimens, about the size of your pinky, you put a notch in it. You can take those grades of steel, put them in that machine, and at -60 Fahrenheit, this hammer swings, and it stops the hammer. That's some tough stuff, right? That's what we want to build out. A good way to mess up your Sharpie machine, too. But that's the kind of steels we can deliver today. 253, we talked about that one this morning. If we have built-up members, say I have an older member or a new member where I have multiple components, well, the member is redundant. It's not necessarily the structure, but the member has redundancy. And then more on the analytical side, looking at system analysis. We have an NCHRP project we're wrapping up, as well as some work for National Steel Bridge Alliance on twin tub girders. That basically, if I have a two-girder bridge, one way I can address this issue of a member failure is to take a member out and look at the dynamic response of the structure and show I have capacity in the faulted state for some interval of time. And so I'll talk a little bit about 1287. This is a project that's trying to quantify and provide guidance on a number of things. First of all, what level of modeling do we need to do for this kind of damage analysis? Do I need to do full, nonlinear material and geometry and time step dynamic analysis? Can I do something simple? So trying to figure out what we need to do so we're kind of standardized. Also trying to give guidance on detailing. If I design a new bridge, there's probably some things I can do to make sure or help improve the performance of the bridge prior to the fracture to mitigate or minimize the likelihood of the fracture, as well as after the fracture that I don't have other problems. How do I tie that into inspection? And where that comes in is if you have a structure, and I mentioned to some of the folks this morning, where we did a test where we used shape charges to sever the lower chord of a truss and look at its system performance. And in statics, it would tell you it would collapse. We had 150,000 pounds of sand on this truss, an old truss from the 20s, 150-foot span. When we cut the lower chord, it deflected 3/8 of an inch. Now, that's good, right? It looks good. But why is that bad? Why is it bad to have a structure have so much reserve capacity? Because what don't you know? You don't know a cord failed. See, it's a one-chord truss. And if you get rid of the other cord, you're going to lose that bridge. I can guarantee that. See, so when I have capacity for this limit state, not having deflection might not be a good thing. You might want deflection for warning, or at least how you address inspection. And then how do we turn that into something people can use in terms of AASHTO? And so we're nearly completed, as I'd indicated. We did a lot of modeling of bridges that have had full-scale fractures. And where there was some instrumentation, we took advantage of it. I mean, people don't generally instrument these because they don't know they're going to fail, right? But some of them, after the fact, there was instrumentation, and there were two, the Milton-Madison Bridge and some work at Texas, where they were explicit tests to look at what happens after the failure. And what we did is we calibrated our approach and our modeling, and a lot of different details of how you model non-composite, how do you model composite. And then we went off and tried some other bridges, some tied arches, and some through-girder bridges that are classic fracture-critical type systems. So a lot of fun analytical work. And as I'd indicated, the system analysis is only part of the story. We need to think about other things in these models, because we're not trying to model crack propagation. We're trying to model the performance in the faulted state. But there's things that affect the life of the structure after the fracture. So the classic example is the Hone Bridge that failed up in Minneapolis, up in Milwaukee a few years ago, about 10 years ago now, where it had details that were susceptible to brittle fracture. And when one of those details failed, it had 3 girders in the cross-section. One of the other girders failed instantly due to the load shedding. It had the same detail that was susceptible. And the other girder failed in the web, the flange state. So it went from being a 3-girder bridge to a single flange bridge. So I can do all the analysis in the world. If I don't recognize that my model isn't too useful, the model isn't too useful, right? If I can't somehow build that in. And so we're not trying to get people to build that in. You take a look at the structure ahead of time, and you determine how much confidence you have in your modeling. Some of these, there's also screening criteria. There's certain bridges we just don't want people doing this on because of challenges. And so it's really, the work is focused on system analysis and how you perform that, but also then guidance on determining if your analysis is reasonable, should it be performed, is it valid, and then long-term inspection strategies. And so a lot of work has been put together to give people guidance on what kind of analysis. We used Abacus, but as long as you follow the procedures and can capture the same type of behavior, it doesn't matter what solver you would use. Gave guidance on material models for concrete and steel and so forth, and guidance on element capabilities. So it's been a lot of fun working on the project, trying to come up with a way to do this. The other challenge, though, is the load model. So we can make that finite element model and say, you know, the bridge will stay up. And the next question that Kevin will be asked when he goes to do this by Federal Highway is, under what load? Is it all lanes loaded? Is it full live load? Is it some reduced live load? So we took a lot of time looking at the load models and what kind of approach should be taken. And we're proposing 2 new load combinations. We call them Redundancy 1 and Redundancy 2. Now notice, they're not called Fracture Critical 1 and Fracture Critical 2. And why do you think that is? It sounds better. We're trying to, for lack of a better way to say it, we're trying to get rid of the blank word, right? Fracture, right? We don't want to use that. Let's put it's redundant. It's Redundancy 1. And it is. It's looking at the redundancy capabilities of the bridge. So we're trying to look at it that way. The first one is attempted to look at when the event occurs and the dynamic amplification of the bridge responding to gravity and a certain set of trucks on that. Then after it gets through that, then there's the extended service. Because the objective, remember, is to change this arm's length inspection interval, to set it in a rational way. So what kind of loading could we expect over some period of time? How do we address that? How do I address the effect of if I don't have deflection or whether I do have deflection? So those 2 load combinations are intended to try to look at that. It's also, I don't know if this is going to fly with the panel, I don't think it will, but the thought of looking at existing and new structures separately. And then, let alone just the load combinations, but how many lanes and transverse positions. So trying to give guidance on that. And then the next is, what's failure? So the bridge gets through these load models. What do you call failure, right? Well, maybe deflection is one thing that's easy. It had too much or it had too little. But what about damage? Now, with these models, you can't really go into AASHTO and calculate a member capacity and compare it to the FE model very easily, right? There's assumptions on effective width and whatnot. Well, the model has all that in it. There's no assumption on effective width, say for a composite girder. And so in this case, we're using a mechanics approaches, right? Looking at stresses, strains, you know, load displacement curves, things like that to try to say, yes, I have enough capacity. So it's a different approach than what would normally be done in AASHTO. And then again, some serviceability criteria. So maybe the structure survives and it has enough strength, but it's on a curve. It's a curved structure and you lose the positive cross slope and now vehicles would tip over. And so we're trying to give guidance like, think about those things. What if a bearing lifts up? It's a complicated, skewed 2-span bridge and a bearing lifts up when a girder fails and somebody crashes into that and gets killed. Well, I don't know, is that redundant? Is it not redundant? And so just giving guidance on that. And some of these things, there is no guidance. Some of it is based on the smoke-filled room, like Robert used to say. You'd get people with experience in a room and say, that seems reasonable, right? You can't do a reliability analysis on how much deck uplift is acceptable. So general findings, we think we've got some good approaches on our benchmark models. Some of these that are classified as fracture critical have a lot of reserve strength, and they don't need to be classified as that. Some, interestingly, didn't meet minimum deflection requirements. They have a lot of reserve capacity. And so that's something to try to step through yet. And then, of course, we think we can then set a rational interval, get away from this 24-month law. Okay, so that's one of the projects. But the other one that's been a lot of fun, it's kind of tying into that, is related to twin tubs. Now, you guys do twin tubs up here? Do many of those?
Yeah, we haven't.
Because of fracture critical, or?
Nope.
No? Okay.
It's all the cross-sections have had multiple tubs.
Okay, okay. So Texas uses a lot, as you know, and Wisconsin has quite a few. And so there's people interested in these girders. It's twin tubs, so you have like a bathtub and another bathtub. And they're deemed fracture critical because there's two. Now there's 4 webs and 4 top flanges, but there's only 2 tension flanges. And so they're, told that they're fracture critical. But they tested one down at University of Texas, and it was quite robust. And analytically, they appear to be quite robust. So NSBA, they're very efficient structures, too, I guess I should mention. They're a nice option for steel. And so the curved versions of these things work out quite well, but you don't need 3 girders if you can get away with 2. It's much more efficient. And so what this project was looking at is, let's analyze a series of structures and try to provide additional guidance, what works, what doesn't work, and so forth. And so one of the things we started finding, same with 1287, is the importance of being able to properly model or reasonably model shear stud pullout. Shear studs end up keeping the bridge up in a lot of cases if you don't have transverse diaphragms. And so in some cases, we would see girders unzipping, which is what they saw in the full-scale test at Texas. And so, developing some basic knowledge on that modeling, we're spending a lot of time in that area, getting shear stud models with multiple studs and different stud heights. And how do you turn that into something that's a simple model so you don't have to do this kind of modeling every time? And so Jem is working on that quite a bit, which is a lot of fun. But other things like, what's failure? Well, is it too much concrete crushing? Well, how much is too much? So trying to develop criteria for that. But most of the bridges had tremendous redundancy. In fact, we're doing some work for Scott Becker down in Wisconsin, where we're analyzing some of his bridges. And we did one with the idea of trying to get the Federal Highway Administration to agree to the approach. They did. And so now he's got one that's taken off the list, and we're going to move forward with using these procedures on a number of his other bridges. But how are we able to do that? Well, you can imagine that, picture, it's inclined tubs on curves, right, with skewed supports. The geometry is a nightmare to do in the FE world, with all the cross bracing and flange transitions and everything that goes into real girders. And so to build one of these models takes a long time. And then you find out you goof something up, and then you got to go back and start over. Well, one of the grad students, Jim Korkmas, he built one, and he said, no, this isn't the way to do this. He said, let me write some Python code. And so he wrote some software to build these bridges, to build these models. And this is how we're able to do these complex models now extremely quickly. Nothing fancy, it's writing code, right? But it really saves time. And I think it's a game changer in how these structures could be analyzed. So it's basic software. You just take a little time to input some geometry, and you can build these in minutes instead of weeks. And so, you start with some input sheets of geometry, kind of step your way through, fill out the form. Actually, it takes longer to fill out the forms, depending on the complexity of the geometry. And once you build this, let's just let this run if this plays, is the software begins to build the bridge. And we hope this is something that we can kind of generalize to make it available to people, because it only runs in Abacus right now. That's the challenge. But through the S-BRITE Center, we're doing a project for Scott, going to evaluate about 12 of his bridges and do the full analysis, and then just show that they hopefully are non-fracture critical. The idea would be to develop a family of bridges, that if I look at enough of them, I can say, if I stay within this box, I can meet these criteria, and I don't have to do this kind of analysis every time. And so that's really what the objective is here, is to analyze enough of them so that we can make that case. So it goes through, and again, you know, this is one of those nice bits of software. Now you can go get your coffee, relax a little bit, let it build the model. And then when you submit it to Abacus, it might take 3 days to run, but to build it doesn't take too much effort at all once you get the geometry. And so our thoughts are we can hand off the sheets to an owner, and then when we're all done, we have a nice little model put together. So now, in honor of Robert, who is an experimentalist, you can't talk about fatigue and fracture without showing some cool fracture tests, right? So the other project is looking at high-performance steel, the steel that has really high fracture toughness. And so I'm just going to show a couple of tests that we did looking at the girders that have high fracture toughness. So we have two setups in the lab, two girders. These are probably about 42-inch deep plate girders that are 40 feet long or so. This one's already fractured. These were fun tests, large tests. Of course, we have to cool them, so it's been a lot of time developing a cooling chamber that we could control the temperature uniformly, then get it off of the specimen so we can test it without destroying the cooling chamber. The folks got really good at doing this, and so let's take a look at one of these fracture tests here. Now, I guess I should say, fractures happen quickly. What we were able to do then is use high-speed cameras to slow this down, and it gives you a feel for how violent. So it's loading. Now this is my crack arrest detail to stop the fracture, because if you blow out the girder, it falls on the floor, and that's not fun. Just watch close as the fracture runs through, and you'll see it come up the web. These are loud. Slow it down to 1 frame per second. You can kind of count as the fracture runs through. If you look here, and then it eventually shoots up the web. These are kind of rare videos to get. These are really neat to have, of fractures running through girders. So we did a whole series of those. The next one was for axial tests, because flexure is a little different than axial, so we built we call it the Sherbden, after Ryan Sherman and Matt Hebden, our axial test machine that's good for a little over 2 million pounds. It's all self-reacting, and we pull specimens apart, and we needed to get cracks in them. Axially, to get them to crack is very difficult, so we'd load them in bending to get a crack. We'd notch it, get a crack, bring it into the machine, cool it. Same thing with a cooling chamber. And I just want to let me just point something out here. This crosshead, I was telling some of the folks this morning, with the specimen and the pin is about 13,000 pounds. This one lets loose, it probably says when he's doing it, at about 850 kips. And just watch the crosshead. There's your crosshead. Okay, lifts right up in the air, throws it up in the air. Now, there's another funny thing in this video. So we do a lot of these kinds of tests. Jason Lloyd is my research engineer. Watch Jason when this thing lets loose and everything shakes. Cool hand Luke, right? Now, what you don't see, there was a visitor from AISC to his right in the other video. That guy jumped about 3 feet. We happen to have a visitor. There we go. Nice bifurcation that arrests. And then we look at this at 1 frame per second. So it starts running, then changes direction. So these are just in here because it's cool, right? These are just neat. But the goal is to try to set new toughness standards so that we can set rational inspection intervals. Again, addressing the idea of fracture from a different point of view. Well, if I have very high toughness material. And so we talked about a different couple of projects. The focus was the system, but the cool videos, I guess, was the toughness. And then this morning, member level redundancy. So we've been fortunate to have a lot of these things kind of wrapping up here around the same time. So hopefully, fracture critical bridge inspection will change in the near future here and become a little more rational. And without hopefully increasing reliability. And there's very innovative designs, efficient designs we can get with, two-girder type systems that hopefully we'll be able to take advantage of. Now, just at the very end here, I wanted to talk a little bit about a center we have at Purdue called our S-BRITE Center. The acronym is Steel Bridge Research, Inspection, Training, and Engineering. And it's 22 acres, but we've developed half, so you're looking at about 11 acres here. And the idea is that when specimens come out of service, entire bridges or specimens, the view was, I thought, well, why do we get rid of them? Why don't we keep them to bring people in to look at for training, professional, undergrad, grad. I can use them for that, but then maybe a colleague who's doing things on non-destructive testing would like to have a bridge, but they can't get out to the bridge. Well, they can do it here using UAVs, whatever you can dream up, right? So the goal is to have other things other than steel. I'm a user of the Center for Aging Infrastructure, but we would like to have other components. But we have some really cool things there. We have a 90-foot span truss that was donated from Michigan. We re-erected it. We've erected everything ourselves, actually, which has been a great experience. And it's got some issues in it, some serious corrosion and welded attachments and whatnot. We plan on putting different types of deck on the truss, so that's fun to have. We have some big plate girders. Now these are our big plate girders. They're 12 feet deep. This is from the Lafayette Street Bridge, and if you look close, very close, you'll see there's no bolts on that little pattern there. These were side-by-side twin girders. A fracture went through this girder and the bridge didn't collapse. This would have been fracture critical. This is a very famous bridge for fatigue and fracture people in the bridge world. We're fortunate, Minnesota provided these girders. They're great teaching tools for us. These were our big girders until we got some really big girders. These are from Dresbach, and Minnesota and Ames Construction were kind enough to cut out pieces at the haunch. Now, the other girders are about 12 feet deep. Dresbach is about 22. There are probably less than 10, I would estimate, bridges in the country that have girders of this scale. They're so big that you couldn't ship them widthwise. You had to lay them on the truck long ways, right? Which limited how wide of a piece we could get. And so we're very fortunate, but also got some pin and hangers from the bridge, some other gusset joints, some bearings. We just had 2 classes down here, and people were just in awe of these, but they're useful other than just looking at. They have some very interesting details on them. And again, we threw those together ourselves. We were able to get some components from 35W. We feel very fortunate about that, and that's going to go into our, when we get our pole barn erected for our forensic specimens. Railroad industry has been very supportive. We have some components from a bridge out of Philadelphia, heavily corroded. How do you like this for a compression member, Ted? This is supposed to be a riveted, built-up compression member, and I don't see the rivets or half of the compression member anymore. So somehow that was still carrying load in compression, but great corroded member. An entire railroad bridge that was on the Pennsylvania Railroad for years, then was in Pueblo, Colorado for years, then got shipped to S-BRITE, and so we re-erected it. And we were able to get railroad ties and rail on it. It's got that railroad bridge smell from the creosote. So it's a really neat addition to the facility. It's got fatigue cracks and a fracture and a whole series of things in it. And we're trying to get our railroad work going further. We've got some signals donated, but we have about 1,200 feet of straight run where we're thinking about trying to put in some track. And some of the BNSF and CSX and NS have said they'd like to try to help us do that. So that'll be fun to do. And then a lot of other different things. And so the reason I'm bringing this up is that it's a neat opportunity to have it. And if you're in the area and if you're down at Purdue and you want to see Bone Lab, it's a great facility to see. But also invite you to come and take a look at the S-BRITE facility because it's a neat atmosphere for training. But it's just neat to get to see some of these components. And so this was a thing that I remember years ago. Dexter and I would be talking about it at 2:30 in the morning in his office, like, why can't we keep this stuff? This would be great to have some of these components. And so it's finally coming to fruition to have some of these things. So with that, I'd be happy to try to answer any questions on the topics. And again, I thank you for the privilege to be able to come and talk to you on this day.
Probably loud enough. Oh, okay.
So watch what you say, huh?
Okay, you mentioned in your presentation this morning that you talked a little bit about inspection and the reliability of inspection.
Yeah.
Could you touch on that a little bit, please?
Sure. Do I have no, that was it. So one of the projects we're doing, are you familiar with this one? Do you know what the results are? No. Oh, okay. I was going to say, you sure you want me to talk about this one? So one of the things that, there was a bridge in Indiana called the Sherman-Minton Bridge that was made out of T1 steel. Had some cracks in it. As you know, sometimes that steel has cracks. And there were inspection issues. And we had to make some serious decisions about keeping the bridge open. And one of the things we had to do was non-destructive testing, in that case, and visual testing. And before we made those decisions, I brought in Glenn Washer from Missouri, who's an NDE guy, expert, and we agreed that we need to get a handle on the variability. So that if somebody says a crack is an inch long or there isn't a crack, we need to know for sure, because we were going to make, again, serious decisions. And we found there was tremendous variability in MT and in UT. All level 2, all accepted, whatever you'd say they need to have, they had. We rejected 1 MT and 2 UT people because they were so out of bounds. And there's no criteria. We had to make up around. And they were pretty liberal, but they still didn't meet it. Which then we noticed in the inspection reports for the visual inspection, there'd be a crack and it would be an inch long. And 2 years later, it'd be maybe, I'm going to say, an inch and a half. And then the next time it was 3/4 of an inch. Then they didn't find it. Then it was back. And that started us thinking, there's variability here. So what we decided to do is we built a bridge that's in the air, so you have to work out of a man lift. And all the boring parts of the bridge, say a plate girder, right, every 20, 25 feet of your cross frames. But between there, it's basically web to flange weld, right? Category B, nothing fancy. If you took all the boring stuff out and squeezed in all the gussets and all the junk, we did that. So that simulates, in terms of details, like 400 to 500 feet of 3 girders. And in there may or may not be cracks. I have to say may or may not, right, because if you come. But there are. And we made specimens with fatigue cracks. So we have a whole series of cracks. Cover plate, out-of-plane distortion, fatigue cracks at gussets, riveted members. And we know where they are. We have the treasure map. And we've sent the inspectors through. And we're at like 27 right now. We want to get up to that 30 number. And the data are not encouraging. That just visual, now not doing anything else. The 50-50 crack, the crack with a 50% probability of detection, is about 1.25 inches. And to get up to the 90% probability, and this is going to change as more data come in, and this is across 12 inspectors, the data I'm quoting, was about 8 inches. We didn't have any crack. We had to project out to get to that. Now, these are just fatigue cracks, and we can break it down by age of inspector, temperature of the day, years of experience, crack type, whatever it might be. But it wasn't very encouraging. And I'm not blaming the inspectors. I think they're being asked to do things visually that are difficult to do. But when I say the 50-50 is that number, there were some inspectors that the longer the crack, the worse they got. I mean, that makes no sense. There were 2 individuals. The bigger cracks, they had a harder time finding them. So the joke was, we'll pair them up with the person who was bad at small cracks or something. So we've talked to the feds about this, and I think we're going to have some more specialized training. That's really what the objective is. But I think it ties into the risk-based, that doing a lot of inspections, I don't think we're getting what we think we're getting, or what they think you're getting. Like, I hate to hear when somebody will say, like, oh, there was a crack and they found it, or something broke and there was an inch crack and they missed it. I don't think that's fair to hammer the inspector for that, because you know the pressures you guys are under to inspect so many of them every 24 months. But doing a lot of frequent bad inspections, not that anybody's trying to be bad, but because of the resources and the time you need to do it isn't there, I don't think that's fair. Other industries have found that if you do less frequent, reliable, in-depth inspections, you're better off to make decisions. So maybe you go every 5 years, but now you can really do a good job on the bridge you want to spend all that time on, because you're not going to the brand new bridge every 2 years where there's nothing. And by the way, if you go often and quickly, you're probably going to miss things. And that's what that would say. There were, at one point, for the riveted details, there were 10 cracks. And the longest crack was up to 1 inch and 3/8, which means part of it was covered by the rivet head. So say 1 inch exposed. Maybe a little more than 1 inch. We had one person miss all 10 cracks. Sounded every rivet. That doesn't matter for fatigue, but he sounded the rivets. And when we said that you missed every crack, he said, well, it was stupid. Why did you even put riveted specimens in here? We never find cracks in those. I know. So once we talked to the person, and it was a good person, they understood that, like, wow, yeah, that's not good. So the crack, and it's only on cracking. We were going to get into corrosion, and this ended up taking all of our time, actually. So what I'd like to see happen down the road, in all honesty, is have 3 more of these frames. Maybe at Purdue, or every state could have one, and you performance test the inspectors to know for sure that there's some level of competency. Because on Sherman Minton, there were people who couldn't find big cracks doing mag particle testing, or they would undersize them tremendously. They're level 2s. You go out and hire a contractor. They've never been performance tested. And we just don't do that. We don't vision test for visual. Now, maybe you all do. Do you guys do any visual acuity tests for your?
I don't know that, but I will find out.
Yeah, and so, no, and again, it's not a criticism, right? But if you think about it, we're doing visual inspection without visual acuity testing. So there's simple things we think we can do. A required flashlight. How you hold the flashlight, right? All those, some simple things I think we can really see an improvement. But at least now we'll have some data to say, gee, that's not likely we're going to find that. If that's the critical crack, and what we'd like to do is then do the same set of tests at night, because sometimes you have to do stuff at night. Well, what is that going to do to your inspection quality? We have no data on that. If it goes in the toilet, I'd like to know that as an owner. We kind of think it might improve, because now they have to use bright flashlights. We'd hope they would. And so, but we don't have the data. So it's the first probabilistic-based study, Glenn and I think, for our industry, looking at bridge details methodically with no, and all this stuff that goes into the human factors portion of it. So not very encouraging, I guess. I don't know. You might disagree, but it.
I agree, but I don't think it goes deep enough.
No, it doesn't. No, we'd like to get into more, but.
I think there's problems where, one, you can identify where usually the cracks form, and they know where to look, right?
Yeah.
That's the important part,
Yeah.
right? So we have that, but there are so many things that all of a sudden show up.
Yeah.
That,
Yeah.
a corrosion that's been happening over 30 years,
Yeah.
and all of a sudden it comes to light.
Yeah.
Okay, where were we looking? Why weren't we looking close enough
I
here?
totally agree with you on that one. What is it? The unique isolated incidents that keep happening. And what he's getting at is, and I deal with these, where they'll find we had a lower cord pull out of a gusset plate on a truss. How can that happen today? They weren't looking at the gussets, right? Now, how can that even happen today, right, with all the attention on trusses? And it was, the corrosion rate, it must have. No, corrosion doesn't happen like that. It wasn't a full thick plate 2 years ago, and now it's gone. They weren't getting up there or whatever. But I think if you could give people the time to spend on that bridge, they would find those things, because they're not inspecting some brand new steel or pre-stressed bridge every 24 months for no reason. So I think I'm hoping this data, we can use it to say we can do some smarter things. So.
The other part I'll throw in, you threw about, loud enough probably, you threw in about.
Day and night.
Yeah.
But think about where we live too, right?
Yeah.
You're dealing from April 1st through,
Yeah.
mid-October, when it's efficient. And if I was out on St. Croix today, you wouldn't want to be out there inspecting in that wind and the cold.
Yeah.
What sort of level of quality are you going to get?
Hopefully, this might make you feel better, but we had inspectors out when it was really hot, and we were down into the upper 20s, and we didn't see a difference. We didn't have a ton of people, right? But of like the majority who were here and the few that were when it was really cold, at least that, we didn't see a big difference. So that was one that we were surprised. Years of experience didn't help. It actually slightly went downward. But
I want to come back to something you said. A few years ago, I was sitting probably in this seat, and
Okay.
we had a seminar, and the conclusion that I was told by the speaker was that their conjecture for the failure of the I-35W bridge was fatigue failure cracking of a particular gusset plate. You just told me that's not true.
I looked at those gussets. I think that's why I was brought in, if I recall. There were no cracks. There was no fatigue cracks, and there was no brittle failure. There was ductile tearing of the gusset plate. It was under-designed. I'm presuming you agree with me. The gusset plate was under-designed by a factor of 2, and as I understand it, it was supposed to be 100 KSI. The plate was made thinner. They switched back to 50, and those 4 fuses never got updated on the drawings. It was purely, it would have happened the next day. And there were other details that were concerned for fatigue, and John Fisher and I were up here looking at them, and there was no issues. So, no, had nothing to do. You can't point the finger at any inspector on that one. No, I don't mean you. I'm sorry. I'm sorry.
I'm just telling you what the speaker told
No,
me.
I'm kind of curious to know who that was, because I might have an idea. But.
Are there other questions?
Make it easy.
Sorry to repeat things if this was mentioned in the internal redundancy discussion this morning, but I'm wondering the NCHRP and AASHTO studies, if you could talk about how are you addressing sort of guidelines for retrofitting a member that has lower strength existing steel with new steel, and say if you have a double channel truss member of say 2 channels of lower strength existing steel, one of the channels fails, and then the new higher strength steel engages together with the remaining existing steel channel. Like how high a plastic strain can that existing steel have in this?
We don't recommend, because we had to look at plastic strains for 1287, right? How much is too much? And we were criticized that we were going too low. I think we were going around 5%. And the reason we were going low is based on experimental tests that we've seen. When you weld, notch, drill, all the local things, you can't get up to your tensile coupon kinds of strain. So we kept it down about 5%, I think. On a real structure, we have not looked at tension members coupled with different strengths of steels. However, Mitt and I did a study for HDR for the Bayonne Bridge looking at compression members. If you go in and strengthen, then you overload, and then you unload, right? So your lower strength steel yielded, your new strength, your other steel, which only had live load in it, right, because you couldn't get the dead load in it. And that's published in the Bridge Journal. But those we've looked at, and they seem pretty forgiving from what I recall, is that when we would load them and then you would unload, now this is all analytical because they were 10 million pounds, I mean, they were huge members, that you could basically reset the clock in each cycle, and then you could start to include it. Now, for the policy part about implementing, was that one of your questions? Yeah. Kind of? So for the built-up member, we had a meeting in Philadelphia in August. Had some stakeholders in the room, and that one is for flexural members at this point, is ready to move forward. So I'll be in Boise in 2 weeks with T18, and we're going to decide how to move forward. Then it'll move to T14 for new design. So the hope will be, if we can get all the ballots through and everybody to say okay, in the next version, member level, well, they call it internal, but member level redundancy will be permitted to set inspection intervals for fracture critical flexural members. That would be for riveted and then new bolted. There'd be 2, the only difference is fatigue provisions, frankly, is the only change. Kathy asked a really good question. Well, what if it's all corroded and there's pack out? Well, I neglected to mention in the morning that there's certain caveats that keep you in a box, and one of them is overall condition. If the member is, you can put your hand through the web, no, we're not going to let you take advantage of this. There's certain fatigue life requirements, plate proportioning requirements. You can't have a 3-inch thick plate, a 3/8 plate, and then angles, because if you lose, right? So pretty much good standard detailing practices. But that one I think can have a potential big benefit on setting rational intervals. So the only thing that has to change is the Federal Highway Memo on fracture critical system analysis, which explicitly says you can't use internal redundancy yet. And it says, because the research isn't done, and so I just need Brian Cozy then to write it and say, hey, it's done, and now you can do this, and if you follow these procedures. So I think we're starting to come together to see something rational with, with this information. But,
Oh, great, thanks.
thank you.
Thanks a lot. Well, the timing is getting a little bit late. I want to leave time for a reception that follows. And also just to make an announcement, there is also a scholarship associated with this event, the Dexter Scholarship. And unfortunately, our scholarship winner had a personal reason who couldn't attend today, but Corin Treat is that scholarship winner. And now I'd like to also mention we have PDH units for our professional engineers who want to take a certificate. They're up front by Professor Labus. If you don't have enough, just leave your card and we'll make sure you have one. And with this, I'd like to again acknowledge our speaker, and then we'll have a reception out in the rotunda. So thank you again so much.
Appreciate it.